Let's look at a few examples of linear algebra ideas in the vector space of matrices M sub Mn. So first of all, let's figure out the dimension of this vector space. So, you know, if you don't know anything else about a vector space, one way of coming up with its dimension is just writing down a basis for the vector space. So what would a basis for the matrices of size Mn look like? Well, you know, we have some number of entries in rows and some number of entries in columns, right? We have n columns here, we have m rows. So there are m times n entries. And in general, it seems like any one of these, right, if all of these were 0, but except for one of them, that would give you a nice basis vector. It would look kind of like the standard basis for Rn, except, of course, this isn't Rn. So what would those matrices look like? Well, there would be 1 and then zeros everywhere else. And then there would be a 1 in the second position in the first row, and zeros everywhere else. And so on, all the way down to zeros in the first row, except for a 1 at the end, and then zeros everywhere else. But that's just for the first row. You could have your non-zero, so zeros in the first row, and then a 1 in your second row, and then zeros after that, and so on, right? All the way down to zeros everywhere except in the very lower left corner, and then zeros, all the way to zeros everywhere except in the lower right corner. So clearly these span M sub Mn, right? Any linear by taking a linear combination of these, you can get any non-zero entry in any position. Are they linearly independent? Well, if we had a linear dependence relationship, right? Any linear dependence relationship among these will have to have, right, when you put a coefficient, say like this, in front of one of these things, when you do this scalar product, that just puts this coefficient in the position where that matrix has a 1. And then when you add all of these things together, all of these, since all of these coefficients end up in different positions, when you add these matrices together, the coefficients never really interact with each other. So when you set this whole thing to zero, the zero matrix, to get a linear dependence relationship, each entry on the left has to be equal to the corresponding entry on the right, but those are all zeros. So each of these a's has to be 0, and so you only get the trivial linear dependence relationship. So these matrices are all linearly independent, and they span, so that means they're a basis. So we have a nice basis for M sub Mn. How many entries are in this basis? Or how many matrices are in this basis? Well, there's one matrix in this list for every entry in every position in the matrix. But how many positions are there? We already said there's m by n, since there's m rows and n columns. So that means the dimension of M sub Mn is m times n. All right. Okay, for another exercise in linear algebra in this vector space of matrices, let's find a basis consisting of invertible matrices. Now, one nice thing about finding bases is if you just more or less randomly choose the appropriate number of vectors, it's almost sure to be a basis. So there's almost sure to not be a linear dependence relationship. So let's just choose some matrices. How about, I don't know, maybe the identity, that's invertible. We could maybe have a 1 down here. This is invertible. We know this is invertible because its determinant is non-zero. We could have a 1 up there. Right? This is also invertible for the same reason. And then, I don't know, how about this matrix? That's also invertible because its determinant is a non-zero. Now, if we choose a basis, we know ahead of time that there's going to be 4 entries because we just showed that the dimension of one of these matrix spaces is m times n, and 2 times 2 is 4. So we have 4 invertible matrices. As long as they are linearly independent, these are sure to be a basis for this space. So how could we show that they're linearly independent? Well, we're going to just have to show that there's no non-trivial linear dependence relationships. So let's write down a linear dependence relationship. How about A plus times this one, plus B times that one, plus C times that one, plus D times this one equals the 0 matrix. Okay, well, if we actually do all of the matrix arithmetic on the left, what we get is, in the upper left corner, we get A plus B plus C plus D. I meant for this to be a D right here. In the upper right, we get, it looks like just C. In the lower left, we get, looks like just B. And then in the lower right, we get A plus B plus C minus D. Okay, and we're saying that this is equal to the 0 matrix. And notice that this gives us 4 equations. This gives us the equation A plus B plus C plus D equals 0. The upper, let's see, lower left corner gives us the equation B equals 0. Upper right gives us C equals 0. And then lower right gives us A plus B plus C minus D equals 0. Now you can see this turns out to be just a system of linear equations in A, B, C, and D. So we could write the augmented matrix for this system and then row reduce it to see what sort of solutions we get. This particular system is actually much easier to solve because the second equation tells us that B is 0. The third equation tells us that C is 0. That means that B and C actually aren't in these two equations. And then A plus D equals 0 and B plus D equals 0. This means that, right, this first equation says that A has to be minus D, and the second equation says that A has to be plus D. But the only way for this to happen is for A and D to also be 0. So A is 0 and D is 0. So the only linear dependence relationship among these matrices is the trivial one. So that means that these 4 matrices are linearly independent, so they span a 4-dimensional subspace. But M22 is 4-dimensional, so the only 4-dimensional subspace it has is itself. So these 4 matrices, they're clearly invertible because their determinants are all non-zero, and they also span the full space M22. All right. Let's have a look at this. Is the collection of invertible matrices in M and N a subspace? What about the collection of non-invertible matrices? Well, the invertible matrices, this is actually pretty easy to check because, right, the very first requirement of a subspace is that 0 is in your subspace. So is 0, the 0 matrix, invertible? No, clearly not, right? So, because its determinant is 0. So 0 is not in this collection of invertible matrices, and so the collection of invertible matrices is not a subspace. So no, not a subspace. Okay, what about the collection of non-invertible matrices? Well, so if we call this collection S, the 0 matrix is in S, so there's some hope. But what other sort of matrices are in S? Typical non-invertible matrices are things that have a kernel, so things that have 0 as an eigenvalue. So here's a good example, right? This matrix is in S, but if this matrix is in S because it's not invertible, well, this matrix isn't invertible either. But the sum of these two things, 1 0 0 0 and 0 0 1 0, sorry, 0 0 0 1, the sum of these is actually the 2 by 2 identity, which is invertible. So here we're violating the closure of a subspace under addition. So that means that the non-invertible matrices also are not a subspace. They contain 0, but they aren't closed under addition. So this just goes to show that some interesting properties in general vector spaces, in certain general vector spaces, don't correspond to being a subspace. So whatever this collection of matrices is, it's not a subspace. It's something more complicated. For our last example, let's have a look at this. So suppose we have a non-zero vector in Rn. Then we can define a map from the m by n matrices to Rm by this. So for any matrix, the output of this function is just that matrix multiplied on the right by V. And this product is defined because the matrix M is m by n, and the vector V is, right, it's a column vector, so n by 1. And so this product is defined, and it produces a vector in Rm because of the m there. So right, this function is defined. The question is it a linear transformation? Well, we can just, right, suppose we have two matrices, say m and n. Then take a linear combination of them and apply this function to them and see what happens. What we need to do is check, is this equal to a times f of m plus b times f of n? Well, let's calculate. F of a m plus b n, that is, right, what this function does is it multiplies on the right by the vector v. But multiplying by a vector, that distributes over matrix addition. So this is AMV plus BNV. But right, matrix multiplication and scalar multiplication associate, so we can throw parentheses in here. But this is exactly what we were hoping it is. So this is a linear transformation, yes. So now, is it onto and is it one-to-one? Well, these are harder questions. One of the reasons that these questions are harder is because this vector, we don't know anything about it other than the fact that it's non-zero. What we could do is extend this to a basis. So say our basis is v and then v1 through v. Turns out we're going to need n minus 1, right? So there are n vectors total, which there has to be because, remember, we're writing a basis for Rn. Okay, now let's define a matrix P by stuffing all of these vectors into a matrix in the way that we're used to doing. Okay, then notice that the inverse of P does something nice for us. When we multiply P inverse times V, what we get is just E1. Right? And this is because P times E1 is V. So P inverse times V is E1. What this matrix is going to let us do is sort of produce some properties in matrices that have certain results after multiplying on the right by V. So let's ask about being onto. So what we're asking is there a matrix M so that M times V is, oh, sorry, I need to state this differently. So for what we need to figure out is for any vector W in Rm, which is the range space, is there a matrix M so that M times V equals W? Okay. So, right, what we need to do is just come up with some matrix here so that this product works out to be W. Well, having V here is a little annoying. If we had E1 here instead, it would be easy to come up with the right sort of matrix. We could just have, right, E1 is the vector that has a 1 in its first position and zeros elsewhere. And multiplying a matrix by E1 just picks off the first column. So to get the result of this product being W, we would just have to put W in the first column here, right? So if we had E1 here instead of V, this would be very easy, right? This would be an appropriate matrix. Let's call this matrix A. Okay, well, the thing is, right, we have this matrix P inverse that sort of translates between V and E1. So if we put P inverse here, and then A, right, then this product is A times, right, P inverse V, that's E1, and then A times E1, we just showed over here that that's W. So what this is showing us is that for M, we can take A times P inverse. Right, so there's some matrix so that multiplying on the right by V gives us W, and this means that this function, this linear transformation F, is onto. Okay, nice. What about one-to-one? Okay, well, remember, one-to-one, that means that different inputs have to go to different outputs. But this, right, matrices have so many entries that this can't possibly be the case. I mean, what we're asking is it possible that we could have different matrices here and still get the same thing after we multiply on the right by V? Well, look, I mean, if we put P inverse here, we know that after you multiply by P inverse, you just get E1, right? So this product is E1. But what if we had P inverse? Oh, P inverse isn't of the appropriate size, so I guess we need to multiply by any matrix. Let's say 0's over here, but has a 1 and then 0's here. Okay, then this matrix, this product is going to be P inverse times V is E1, and then this product is just going to pick up this first column, and that's going to give us the column vector that has a 1 just in the first position. Is there any other matrix we could put in this position to make this happen? Well, you know, when we work this out, the stuff in this position, all the zeros here, actually didn't matter because E1 has a bunch of zeros in it that was going to zero that stuff out anyway. So we could put a 1 here and zeros here, and then, I don't know, put anything else in here, right? Anything non-zero. Then this product is going to be 1 with zeros down the first column, and then anything in there. P inverse times V is E1, and then this product is, again, a 1 with nothing but zeros. So here we have two different matrices that give us the same thing after multiplication on the right by V, and that means that F is not one-to-one.